Hello, and welcome to the Current Science and Technology podcast from the Museum of Science in Boston. I'm your host, Susan Heilman, and every week we bring you interviews with guest researchers and our museum staff covering science and technology in depth. Nano Days 2015 has come and gone once again, and this year one of the highlights of our event was the viewing for the first time of a film called From Lab to Fab, Pioneers in Nano-Manufacturing. I was able to speak with the director of the movie, Larry Klein, just the other day. And right now, I'm lucky enough to have with me the two pioneers in nano-manufacturing. I have entrepreneur Peter Antoinette, president of NanoComp, and engineer Ahmed Bousnena, the director of the Center for High-Rate Nano-Manufacturing and professor at Northeastern University. Hello, gentlemen. Thank you for joining me.
Hi, Susan. Hi. Thanks for having us.
First off, this is the first time both of you were able to see this movie. What did you think of how it came out?
It came out great. I think Larry did a really great job. Told a good story, captured most of the things that we see every day, but we don't notice.
Yeah, it was very impressive because it does illustrate, I think, two stages. One of NanoComp, which is exited the real startup phases in the expansion role, and NanoOps, which is really trying to pioneer maybe one of the older technologies, offset printing, into one of the most modern applications, nanotechnology and sensor systems. Really a great way to capture that.
Yeah, and what I like the best about it is that he told a story, and it wasn't just, this is the technology, this is how you make it. You actually get involved in the storyline of what you're doing and how you made the transitions from taking the academic knowledge of nano and transferring it into scaling up something that's nano-sized up to a really huge size. So, Peter, you got your foot in the door, relatively speaking, early on this nano-manufacturing. So if you could give us a little bit about your company, what you guys make, and why you thought that'd be a good idea 10 years ago.
Well, we got started looking at carbon nanotubes. They have remarkable properties in publications, very strong, high-strength materials, conductive electrically, seemingly would have the ability to solve a lot of economic problems, being able to be useful. But one of the things you have to do is be able to get them in volumes that are useful. For example, in a shirt that we'd wear every day, there's 10, 12 kilometers of yarn. So if you're going to go out and make a material that's going to be in shirts or, in our case, bulletproof vests, you have to be thinking hundreds and thousands and, in fact, millions of kilometers of material, which actually turns out to be tonnage-type quantities. We're involved with lightweighting composites for aircraft and in spacecraft. So, again, tonnage quantities is the way you have to think.
And how long it could take to make something like that. So what is the material you're using? I mean, it's nano-sized.
Yeah, carbon nanotubes look like a chicken wire. And if you roll it up into
on the nanoscale,
yeah. Right? But if they look like it, just what it looks like. It kind of looks like that. Roll it up into a cylinder and pop a little cap on the end, but then shrink it down to the diameter of DNA. Mm-hmm. So the individual tubes that we're working with are effectively the size of DNA. So you have to make trillions per second or more and be able to put them in a format that's actually useful. So we spin them into yarns and fibers.
Right, but then you don't have a nano-sized loom or weave. You're not weaving them together. So how do you get a two-dimensional cloth?
Right. So you at the nano scale, they're actually entangling. They're bundling up and they're entangling with each other, forming a very strong structure. And then we bring them out of basically a 6-inch tube furnace out and either spin them directly out of there, almost like spinning smoke.
Yeah.
Looks like black
looks
cotton
like
candy.
I thought it was smoke when I saw it before I realized what it was.
Yeah, or black cotton candy, and you spin it into a fiber or lay it down onto a belt to make a non-woven sheet. Think now making these in the hundreds of kilometers long, or sheets that are hundreds of feet long and 4, 5, 6 feet wide.
And so you mentioned a couple areas that you're using it in, that they're lightweight and strong, like for aircraft, and also lightweight and strong, again, for things like bulletproof vests. So can you tell me a little bit about where are your materials right now?
We've worked with a company that just introduced a lightweight vest to the police forces of the U.S. Think about the thickness of a folded over lapel of a sport jacket. That's the thinnest, lightest that's ever been put out there.
And it's movable too. It's not like you're in a stiff coat.
Yeah, you got it. It's flexible, lightweight, comfortable. So that the important part of that is, the August, any place in the U.S. virtually where it's hot and
even
humid.
Boston.
Yeah, even Boston. Not this year yet. We're waiting for August, but even Boston, and where you'd wind up, a police officer might just decide to leave that vest home.
Because it's too hot and
Because it's
bulky.
hot, bulky, uncomfortable. So for us, we're really thrilled that we could offer something that's lighter weight and offer the equal, or in fact, even better protection. That kind of material is also being used in aircraft today. And in spacecraft, we're actually on the Juno spacecraft, a $1.5 billion satellite going to Jupiter, going to get there next year. And we're protecting the main engines on it with our materials. It's a thrill to be able to do things like that.
Now, it's lighter weight, so that makes sense on a spacecraft to have the lightest weight material possible. But there's been other lightweight materials. Is there anything else special about your material?
Yeah, that's a great point. The fact that it's also electrically conductive. That we were able to have that lightweight, high strength, and be electrically conductive. This was enabling the protection from the heavy-duty radiation around Jupiter, which are about 1,000 times that of the Earth. Our material was one of the only materials that was going to get through that, and a protective way to protect the engines. The engines got to work.
Yeah.
So that's why we're there.
That's amazing that you can everything from right here on Earth, protecting people, and then protecting spacecraft.
Yeah, it's terrific.
So, Ahmed, you're still getting your foot in the door with scaling up this manufacturing, but you didn't just start in nano. You've been researching nanomaterials for a really long time. What was your research in, or is it in? I'm assuming you're still doing it. And why did you decide that you needed to scale it up to this manufacturing level?
Well, I started more than 30 years ago in the semiconductor industry. So this is making the regular chips that you see today, for example, in your phone and your laptop and so forth, and in your car even. And I did that until almost 2000. And when I started working in nanomaterials, which was about that time, I said, well, these are great material, great product, but no one has any idea on how to build chips or devices or sensor out of them. And I looked at, because I came out of the semiconductor industry, I knew how to build stuff, and I said, well, that's not going to work. There got to be a new way to do this. And we started working on that and trying to make things out of it, a transistor, an inverter, a sensor, a variety of things.
And you were able to do that on a small scale in your lab.
That's right. And it turns out a process that's similar to printing was the best way to do it. And it was so flexible that you can use any nanomaterial, for example, to do that. But the scale that we used to work is a centimeter scale. The biggest one will be 1 centimeter by 1 centimeter, for example. And also the process that was used was physical chemistry type process. It's very sensitive to a lot of things. And so depending on the student that use it, you could have a yield of 90% or you could have a yield of 5%.
And
so
you need 100%.
You need 100%.
To get this.
Well, or 99. We'd be happy with 95.
Okay.
So basically, we wanted to look at scaling up. How do you make it from 1 centimeter to about 15 centimeter, for example, or larger?
You need a lot of grad students
That's
to
right.
do that.
Yeah, and the companies would not hire our graduate students to do that. So we needed to build an automated, large scale production facility, and so we thought about using similar technology to what the semiconductor industry is using, but using the new nanoscale printing process. And so that's when we started working with Belara, and the movie covered from the very beginning, when we started with the design stage all the way to the finished prototype that actually was doing the printing. And the idea was to automate everything: the recipe, the handling, the alignment. Everything has to be handled by the machine. And so the operator, all they have to do is just provide the material and let the machine do the printing, for example. And that would be the only way for this to be in commercialization or in production, is to have a fully automated process where you know what the yield is, you have repeatability and consistent production and so forth. And it can produce, we did an estimate that in full production, you can make you can actually get it up to make millions of devices per second if they're small enough.
That's
Yeah.
absolutely amazing. Wow. I'm just trying to wrap my head around the fact. So you're going from academia into a production world.
Yes.
And that's not something that maybe you are, but your whole team, you need to get this other group, this robotics group in. But how much are you working to get? Did you just say, hey, robotics group, make this for us? And then you said, we'll see you in a couple months, and then carry on.
No, it doesn't work like that. We had to work with them for more than 8 months to put the design together, and we were on every stage of the design we had to give, because the process is ours. They know nothing about our process, and we don't really know how they do stuff. Even though I used to teach design a long time ago, but it's still way beyond what I taught. And so we worked together for more than 8 months to put it together, and it took a long time because it was first time design, first time building it. So it was the very first prototype. And so it took a long time, but it at the end it did work. And you see the movie, actually it stopped working right before the unveiling.
Yep.
and then they made it work. So there's a lot of software that goes in there. There's a lot of automation. There's a lot of reference points that you have to align that when you pick up the template, the robot doesn't know which end is up, for example. So I had to align it, and then had to align it.
So there was a human
That's
part of it as well.
No, it's all automated.
Oh, it is? Oh, okay.
It's all
So
automated.
even the
Yeah,
aligning
yeah,
of
yeah.
it.
So
the
there's a
robot is able to
pre-aligner,
do
and
that.
then there's a liner.
Okay.
Yeah, and so the machine is designed to work with nanotubes, designed to work with nanoparticles that are metals, nanoparticles that are semiconducting, nanoparticles that are insulators, designed to do
And
polymers.
all in potentially the same
Polymers.
circuit.
That's right. Yeah, and so the assembly process is a physical chemistry process. There's no chemical reactions, so that means you can pick up any material you want and actually make a device out of it. But it's not just devices. It's not just electronics. Electronics is only one application. You can make sensors. You can make energy harvesting or energy storage. You can make composites, type of composites that mostly nanotube type composites. You can make composites that have embedded sensors that both use nanotubes, for example. You can make. We now have a project to make drugs, for example. These are cancer drugs that are printed and molded so that a lot of the cancer drugs and also a lot of the other drugs are insoluble, which means you have to inject. You cannot take orally.
Right.
And so by printing the drugs in a very small nano size, you can put them in a pill, and you can actually take the pill, and these drugs will go through the stomach or the intestine walls directly to the blood. And so you don't have to take an injection ever.
So your next step here is, I understand it's finding investors to be able to do this, but are you talking to other people you know in academia? Like, who would make use of this? So investors to put money into this, but I mean, you're not going to sell this to other labs to build stuff for them. You're going to sell this to companies that already have an interest in drug manufacturing or an interest in making sensors and things like that. Is that correct?
Yeah. Let me be clear. We don't have a company that would sell this right now.
Okay.
I mean, this is done joint work between the two. This is the first prototype. We may actually make 2 or 3 other prototypes to just add some improvements. But right now, we're making this available to companies to come in and print their own product.
Okay.
Okay, and have more strategic collaboration or strategic partnerships. Now, we already have large companies come to us, and they said, we want to use this.
Right.
And so in some cases, the application you can think of. In some cases, you don't even know. The customer knows the application is.
Right.
They come to you. And so that's the case. We have a company that came to us with an application that we never thought of. Says, oh, you want to do this? Why would you want to do that? Well, because there's a big market for it.
Right.
And so we're available for companies to do that. So what we can do is print at the nanoscale. Now, let me give you an idea. I mean, printing electronics is not new. Companies have been doing it for 10 years. And a lot of the antennas in your iPhone or your smartphone are printed. There's a lot of circuits that are printed that you buy. The Kindle, for example, the reader, that's printed. But the problem with the printed electronics today is that the scale they do, which is 20 micron, is the same scale that the silicon chips were using 40 years ago.
Oh.
So they're stuck in 1975 scale. This one would put them in today's scale, for example. And so we know that that's very advantageous, but also more so, it can use the